In this lesson, we're going to start out by looking at multinomial distribution, and then we're going to follow it up looking at the Poisson distribution. Now think about what we just did with the binomial distribution. When we think of this starting by, we're thinking of two terms, success and failure. In this case, we're talking multi. We're talking a lot of things that could occur. The formula for this is going to be, and this is going to look complex, n factorial over x1 factorial times 2x2 factorial for as many x's as I have. And that looks complicated. We'll go through it in 1 second. Then you're going to take that and you're going to multiply it by the probability of the first event, by the number of events that I expect, times the probability of the second event, times the number of second events, all the way down, again, for the number of events that I have. N in this case is your total number of trials, just like it was in the binomial distribution. Your different x's would be your number of successes, since it's x sub 1 for the first item we're looking at. X sub 2 would be for the second item I'm looking at, and so on and so forth. And then P1 would simply be the probability that X1 occurs, or P2, the probability that X2 occurs, and you do this for as many as you can. Let's look at one example, because this will make a lot more sense with an example. In this situation, I have four things that could happen here. I have the people that have a dog. The probability of that happening is 0.3. The probability that they have just a cat. The probability that they have both. And then because it says everything left over, the probability that they'll have neither. Remember, all these have to add up to 1. Well, we're looking at 10 items here, so my n value is going to be 10. Then they're asking me for 3 having a dog. Well, that's the situation here, x1. So x1 in this case is 3 of the 10. 2 having a cat, so my x sub 2 is 2. 1 having both, and the rest, which 3 plus 2 plus 1 is 6, we're coming out of 10, would have nothing. Now we're going to go back to the formula. If you think of the formula, the first part is the n on top, factorial. Then it says take all your x's and write them out as factorials. So x1, x2, x3, x4. Then you're going to take that whole thing when you get it, and I would suggest putting this in your calculator first, and you're going to get 12,600. Just be very careful when you put it in. And then you're going to multiply that by the probability of x occurring, by the number of x's I expect, the probability of x2 occurring, having a cat, and the number of people with cats, and I file it right down the list. And now very carefully I put this all on my calculator, and if you do it right, that's the answer that you'll get. So again, multinomial distribution, we're looking at the idea that instead of 2 events, in this case there's 4, but there has to be more than 2 events. We'll look at another example in class. So that brings us to the Poisson distribution. Poisson is not that much different than binomial in what it does. The difference is we use this when n is a very large number and the probability of success is very, very small. And the formula is going to look like this. I'm going to put some funny looking things up here. Where E is the constant term, this, the Greek letter gamma, is your number of expected occurrences, and x is the number of successful occurrences. Gamma does not have to be a whole number. It could be, but not necessarily. And remember, this is the constant term e. You have that key right on your calculator. Use it, just like pi. Again, formula looks confusing. Let's look at an example. In a large company, it is estimated that only 0.7% are over the age of 70 for the workers. In this case, we're looking at the probability of success of being 0.007. Remember, 0.7 turned into a probability. That's very, very small, and we're looking at a substantial amount of people here. Well, to find gamma, gamma is an expected, gamma is an average. All I have to do is n times p, just like we did before. So in this case, you would take 350, and you multiply it by 0.007. So of the 350 people that work in the company, I would expect 2.45 of them to be over the age of 70. Again, gamma does not have to be, and in most cases, it will not be a whole number. It might be. So now we're going to find the probability that exactly 3 people are over 70 years old. Well, there's my x. So I go to my formula, e, remember that's a constant term, to the negative gamma, so negative 2.45. I'm going to multiply that by gamma, the expected occurrences, to the power of 3, in this case the number of occurrences I'm looking for, and all that over 3 factorial. Again, put this in your calculator very, very carefully when you put this in. Make sure you have exponents going where they're going, and what you'll end up with is probability of 0.21, which makes sense because I'm looking for 3 people, and that's pretty close to the expected number for the entire company. Again, I know one example is not going to make you a world beater in this, but we'll get to that point.